When a 4-pole automatic transfer switch, often referred to as an ATS, is utilized to connect a generator to a main electrical system, neutral switching becomes a critical safety feature. The primary purpose of neutral switching is to enable the ATS to isolate the main electrical system from the generator, specifically in the event of a ground fault. In normal operation, the ATS connects the main electrical system to the generator. This connection involves all 4 poles, which are the 3 phases labeled low L2 and L3, as well as the neutral conductor. Now, when a ground fault occurs on the generator side of the system, the ATS is designed to detect an imbalance. This imbalance is between the return currents flowing through the neutral conductor and the currents in the individual phases. The detection of this imbalance serves as an indication of a ground fault. Once a ground fault is detected, it triggers the neutral switching mechanism within the ATS. The ATS responds by opening the neutral connection. This action effectively isolates the generator from the main electrical system. By isolating the generator, the ATS prevents the fault current from flowing back into the main electrical system. This is crucial for protecting equipment and preventing injury to personnel who may be working with or around the electrical system. There are additional benefits of utilizing neutral switching in this type of setup. Firstly, it provides improved generator protection. By isolating the generator from a ground fault, the neutral switching mechanism prevents the generator from being damaged as a result of overcurrent conditions. Secondly, it reduces the risk of electrical fires. By preventing fault current from entering the main electrical system, neutral switching significantly reduces the risk of electrical fires or explosions that could result from the fault. Thirdly, it enhances overall system reliability. Neutral switching ensures that the main electrical system remains operational, even in the event of a generator fault. This provides uninterrupted power to critical loads that rely on the main system. Neutral switching is typically required when connecting a 4-pole generator to a main electrical system. This requirement is particularly important in applications where the main electrical system is grounded. This includes systems that are solidly grounded and those that are resistance grounded. Neutral switching in 4-pole ATS for generator connection is a critical safety feature. Its main function is to protect the main electrical system and personnel from the potential dangers of ground faults by isolating the generator when a fault is detected. To delve deeper into this topic, let's clarify some of the technical aspects of ground faults and neutral switching. A ground fault occurs when an unintended electrical path is established between a live conductor, which could be one of the phase conductors, and ground or a grounded object. This can happen due to various reasons such as insulation failure, physical damage to wiring, or even moisture ingress. When a ground fault occurs, a large amount of current, known as the fault current, flows through this unintended path to ground. This fault current can be very dangerous, posing a significant risk of electrical shock, fire, and equipment damage. In a typical electrical system, the neutral conductor is intended to carry the unbalanced current between the phases. However, under normal operating conditions, the current flowing through the neutral conductor is relatively small. When a ground fault occurs, a significant portion of the fault current may return through the neutral conductor, creating an imbalance between the phase currents and the neutral current. This imbalance is precisely what the ATS detects to initiate the neutral switching process. The ATS utilizes current transformers or other sensing devices to monitor the current in each phase conductor and the neutral conductor. These current transformers provide a signal to the ATS control system, which continuously analyzes the current levels. When the control system detects an imbalance that exceeds a predetermined threshold, it recognizes this as a ground fault condition. The threshold is set to ensure that the ATS responds quickly to a genuine ground fault while avoiding nuisance tripping due to minor imbalances. Once a ground fault is detected, the ATS activates its neutral switching mechanism. This mechanism typically involves a dedicated switch or contactor that is specifically designed to interrupt the neutral connection. The switch is usually a robust device capable of handling the full rated current of the system. When the neutral switch opens, it breaks the electrical path between the generator neutral and the main system neutral. This isolation prevents the fault current from propagating into the main electrical system. The effectiveness of neutral switching depends on several factors, including the speed of the ATS response, the quality of the neutral switch, and the overall design of the grounding system. A fast response time is crucial to minimize the duration of the fault current and reduce the potential for damage. The neutral switch must be capable of reliably interrupting the fault current without failing or creating additional hazards. The grounding system should be designed to provide a low impedance path for fault currents to flow back to the source, which helps to facilitate the detection and clearing of ground faults. In addition to the safety benefits, neutral switching can also improve the performance and reliability of the generator. By isolating the generator from ground faults, it reduces the stress on the generator windings and other components, which can extend its lifespan. It also prevents the generator from tripping offline due to ground fault protection, which can disrupt power supply to critical loads. When considering the implementation of neutral switching, it is important to consult with qualified electrical engineers and adhere to relevant standards and regulations. These standards provide guidance on the design, installation, and testing of ATS systems with neutral switching capabilities. They also specify the requirements for grounding, bonding, and overcurrent protection. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, including those involving generators and transfer switches. Article 710 covers emergency systems, while Article 701 addresses legally required standby systems. These articles outline the requirements for transfer equipment, including automatic transfer switches, and the need for isolating the normal source from the alternate source. Sections 710D and 701. 10D specifically address the transfer of neutral conductors. It states that the neutral conductor of an emergency or legally required standby system shall be switched unless certain conditions are met. These conditions typically involve ensuring that the ground fault protection system is coordinated to prevent unwanted tripping and that the neutral conductor is adequately sized to carry the maximum possible neutral current. Furthermore, it is important to consider the specific grounding configuration of the electrical system. In solidly grounded systems, the neutral conductor is directly connected to ground at the service entrance. In this case, neutral switching is generally required to prevent ground fault current from circulating between the generator and the utility source. In resistance-grounded systems, a resistor is inserted in the ground path to limit the ground fault current. In this case, neutral switching may not be required if the resistor is sized appropriately and the ground fault protection system is properly coordinated. However, it is still recommended to use neutral switching in many resistance-grounded applications to provide enhanced safety and reliability. The selection of the appropriate ATS with neutral switching capabilities depends on several factors, including the size of the generator, the voltage and current ratings of the system, and the specific application requirements. ATS are available in various configurations, including open transition, closed transition, and soft loading. Open transition ATS interrupt the power supply before transferring to the alternate source, which can cause a momentary interruption of power. Closed transition ATS provide a momentary paralleling of the two sources before transferring, which can minimize the interruption of power. Soft loading ATS allow for a gradual transfer of load between the two sources, which can reduce stress on the generator and the electrical system. The installation of an ATS with neutral switching should be performed by qualified electricians who are familiar with the specific requirements of the system. The installation should be carefully inspected and tested to ensure that it meets all applicable standards and regulations. Regular maintenance and testing of the ATS are also essential to ensure its continued reliable operation. This includes inspecting the contacts, checking the control system, and testing the neutral switching function. In conclusion, neutral switching in a 4-pole ATS is a crucial safety feature that protects electrical systems and personnel from ground faults when a generator is connected to the main power grid. By isolating the generator's neutral from the main system's neutral during a fault, it prevents dangerous fault currents from propagating, reducing the risk of electrical fires, equipment damage, and electrical shock hazards. When considering neutral switching, always consult with qualified electrical engineers and adhere to the latest edition of the National Electrical Code, as well as other relevant industry standards to ensure safe and compliant installation. Remember that proper grounding, bonding, and overcurrent protection are also essential components of a well-designed electrical system. By implementing these measures, you can significantly reduce the risk of electrical hazards and ensure the reliable operation of your electrical equipment. Now, let's consider some practical examples of how neutral switching is applied in different settings. In a hospital, for instance, the generator is often used to provide backup power to critical life support systems, lighting, and other essential equipment. In this case, neutral switching is essential to ensure that a ground fault on the generator does not disrupt the power supply to these critical loads. The ATS would be configured to automatically transfer to the generator in the event of a power outage, and the neutral switching mechanism would isolate the generator from the main system in the event of a ground fault. This would ensure that the hospital's critical systems continue to operate without interruption. In a data center, a generator is used to provide backup power to servers, networking equipment, and other critical IT infrastructure. In this setting, even a brief interruption of power can have significant consequences, such as data loss and downtime. Therefore, neutral switching is essential to ensure that the data center's power supply is as reliable as possible. The ATS would be configured to provide a seamless transfer to the generator in the event of a power outage, and the neutral switching mechanism would protect the data center from ground faults. In an industrial facility, generators are often used to power critical production equipment, such as motors, pumps, and control systems. In this environment, a ground fault can cause significant damage to equipment and disrupt production processes. Neutral switching is used to protect the equipment and maintain production uptime. The ATS would be configured to transfer to the generator in the event of a power outage, and the neutral switching mechanism would isolate the generator from the main system in the event of a ground fault. This would minimize the impact of the ground fault on the production process and prevent costly downtime. Let's take a look at the specific components and wiring configurations involved in neutral switching. A typical 4-pole ATS with neutral switching includes the following main components. Firstly, a control system that monitors the voltage, current, and frequency of both the normal power source and the generator power source. Secondly, a switching mechanism that consists of 4 sets of contacts, one for each phase conductor alone, L2, L3, and one for the neutral conductor. Thirdly, current transformers that are used to measure the current in each phase conductor and the neutral conductor. Fourthly, a ground fault relay that monitors the imbalance between the phase currents and the neutral current. Fifthly, a neutral switch that is specifically designed to interrupt the neutral connection in the event of a ground fault. The wiring configuration of the ATS with neutral switching is as follows. Firstly, the 3 phase conductors and the neutral conductor from the normal power source are connected to the corresponding terminals on the ATS. Secondly, the 3 phase conductors and the neutral conductor from the generator power source are connected to the corresponding terminals on the ATS. Thirdly, the current transformers are installed on each phase conductor and the neutral conductor to measure the current flowing through them. Fourthly, the outputs of the current transformers are connected to the ground fault relay, which monitors the imbalance between the phase currents and the neutral current. Fifthly, the output of the ground fault relay is connected to the neutral switch, which is activated to interrupt the neutral connection in the event of a ground fault. When installing an ATS with neutral switching, it is important to ensure that the wiring is done correctly and that all connections are secure. It is also essential to verify that the ATS is properly grounded and bonded to prevent electrical shock hazards. Regular maintenance and testing of the ATS are crucial to ensure that it continues to operate reliably. This includes inspecting the contacts, checking the control system, and testing the neutral switching function. Now, let's consider some advanced concepts related to neutral switching. One such concept is the use of harmonic filters to reduce the amount of harmonic current flowing through the neutral conductor. Harmonic currents are caused by nonlinear loads such as electronic devices and variable frequency drives. These currents can cause overheating and other problems in the electrical system. Harmonic filters can be used to reduce the amount of harmonic current flowing through the neutral conductor, which can improve the performance and reliability of the electrical system. Another advanced concept is the use of advanced ground fault protection schemes to provide more sensitive and reliable ground fault detection. These schemes may involve the use of multiple ground fault relays, differential protection, or other advanced techniques. These schemes can provide faster and more accurate ground fault detection, which can reduce the risk of equipment damage and electrical hazards. In addition to the technical aspects of neutral switching, it is also important to consider the economic implications. The cost of an ATS with neutral switching can be higher than the cost of an ATS without neutral switching. However, the benefits of neutral switching, such as improved safety, reliability, and equipment protection, can often outweigh the additional cost. It is important to carefully evaluate the costs and benefits of neutral switching before making a decision. Furthermore, it is important to consider the long-term cost of operating and maintaining the ATS. Regular maintenance and testing are essential to ensure that the ATS continues to operate reliably. These costs should be factored into the overall economic analysis. Neutral switching is a critical safety feature in electrical systems that utilize generators as backup power sources. It protects equipment and personnel from the hazards of ground faults by isolating the generator's neutral from the main system's neutral when a fault is detected. This prevents dangerous fault currents from propagating, reducing the risk of electrical fires, equipment damage, and electrical shock hazards. By adhering to relevant standards, consulting with qualified professionals, and implementing proper installation and maintenance procedures, you can ensure the safe and reliable operation of your electrical system with neutral switching. The benefits of neutral switching, such as improved safety, reliability, and equipment protection, can often outweigh the additional cost. Let's talk about the specific types of generators that often require neutral switching. Generators used in emergency standby systems, such as those found in hospitals, data centers, and other critical facilities, typically require neutral switching. These generators are designed to provide backup power in the event of a power outage, and neutral switching is essential to ensure that the backup power system is as reliable as possible. Generators used in legally required standby systems, such as those found in fire alarm systems and emergency lighting systems, also typically require neutral switching. These generators are required by law to provide backup power in the event of a power outage, and neutral switching is essential to ensure that the backup power system meets the legal requirements. Generators used in optional standby systems, such as those found in residential homes and small businesses, may also benefit from neutral switching, although it is not always required. These generators are used to provide backup power for convenience or to protect against economic losses, and neutral switching can provide an added layer of safety and reliability. In addition to the type of generator, the specific grounding configuration of the electrical system also plays a role in determining whether neutral switching is required. In solidly grounded systems, where the neutral conductor is directly connected to ground at the service entrance, neutral switching is generally required. In resistance-grounded systems, where a resistor is inserted in the ground path, neutral switching may not be required if the resistor is sized appropriately and the ground fault protection system is properly coordinated. However, even in resistance-grounded systems, neutral switching is often recommended to provide enhanced safety and reliability. Now, let's discuss the importance of proper coordination between the ATS and the generator. The ATS and the generator must be properly coordinated to ensure that the backup power system operates reliably and safely. This includes ensuring that the ATS is compatible with the generator's voltage, current, and frequency ratings. It also includes ensuring that the ATS is properly configured to transfer to the generator in the event of a power outage and to transfer back to the normal power source when the power is restored. The coordination between the ATS and the generator also involves ensuring that the ground fault protection system is properly coordinated. The ground fault protection system must be designed to detect ground faults quickly and reliably and to trip the appropriate circuit breakers or fuses to clear the fault. The coordination of the ground fault protection system is particularly important when neutral switching is used, as the neutral switch can affect the way that ground fault currents flow through the system. In addition to the technical aspects of coordination, it is also important to consider the operational aspects. The ATS and the generator should be operated and maintained in accordance with the manufacturer's instructions. Regular testing and maintenance are essential to ensure that the backup power system is ready to operate when needed. Operators should be trained in the proper procedures for starting, stopping, and transferring between the normal power source and the generator power source. In conclusion, neutral switching in a 4-pole ATS is a critical safety feature that protects electrical systems and personnel from the hazards of ground faults when a generator is connected to the main power grid. By isolating the generator's neutral from the main system's neutral during a fault, it prevents dangerous fault currents from propagating, reducing the risk of electrical fires, equipment damage, and electrical shock hazards. When considering neutral switching, it is important to consult with qualified electrical engineers and adhere to the latest edition of the National Electrical Code, as well as other relevant industry standards to ensure safe and compliant installation. Remember that proper grounding, bonding, and overcurrent protection are also essential components of a well-designed electrical system. By implementing these measures, you can significantly reduce the risk of electrical hazards and ensure the reliable operation of your electrical equipment.